All right, now we're in the last topic or subtopic, I guess you would say, of this chapter topic, the first law. This is adiabatic changes. Remember, adiabatic means no heat, right? No heat is being allowed to transfer. That's an important part here. So this is just a lot of little derivations. That's how we're going to work it. All right, so thinking about what no heat means. And if we remember way back when, right, delta U is going to be Q plus W, right? That's internal energy, right? But if adiabatic means that Q is 0, that means delta U equals W, just work, right? But we also said that our delta U at constant, our delta U is also going to be CV delta T. If you went back to the first topic of this, the internal energy, that's part of what we derive from that, right? So our work here, we'll call it adiabatic work, is going to be CV times delta T, right? Now we also know, of course, that one of the definitions of work is that it's also negative P dV, right? It's the change in volume at a constant pressure, either external pressure or the internal constant pressure, right? And if we insert into this, we take PV equals nRT, insert it into our value for pressure, and what we get CV delta T left-hand side, right? On the right-hand side, we'd get negative nRT over V dV, right? Negative nRT over dV. Right. And then we can we'll move the temperature over to the other side, right? Because this already has temperature, right? And so we can kind of go from there. We'll change this to dt, make it in the more proper form, because we haven't done any. If we have dv's, we'll keep dt's on the other side, right? So we'll move t over here, and then divide that by t, right? So if we look at it, rearrange it a little bit, what do we have on the left-hand side? Oh, come on, I'm trying to erase it. Well, okay. We have negative nr times dv over v, right? Negative nr over times dv over v. Now, if we wanted to integrate this expression over a change, and over here we have change in temperature, a change in volume, right? On the left-hand side, the temperature, we go from initial temperature to a final temperature, right? CV is just going to be a constant in this case. We're going to assume it's a constant over this temperature range, right? And so we're going to have the integral of dt over t. On the right-hand side, we do the same thing, the change in volume. Negative n times r is going to be constant. And so we'll have some initial volume and some final volume of dv over v. And when you do each one of these things, right, what are we going to get? Well, the integral of 1 over t is going to be cv times the natural log of df minus ti, right? The integral of 1 over t is natural log of t. But when we go from ti to df, we have to do this, right? Tf on top of our natural log here. And over here will be negative natural log of r. Same thing, natural log now of vf over vi. Right. And then from there, if we move everything, like all the constants, to one side, right, our constants would be cv over negative nr, right, cv over negative nr. right? And then we can also flip, we'll take out that negative and we'll use it to flip the sign. So basically, natural log of TF over TI. And over here, we're gonna like use this negative to flip the natural log, make it VI over VF, right? Because the negative becomes a -1 exponent, right? Because of our logarithmic properties. And the -1 exponent of a fraction flips the fraction, right? So we flip the fraction here inside, right? So now we have two sort of little functions here. We have a constant here, CV over NR, times the natural log of TF over TI, equaling the natural log of VI over VF. Right. Now from here, what we can do to make it look very, very common, all right, we can use our logarithmic properties again and say, okay, this constant here, I can make it into an exponent of our natural log. So basically we say natural log of TF or TI, and we're going to say some constant C, right? In this case, C is going to be equal to CV over NR, right? All the stuff that we're just taking CV over NR and shrinking it down into a little c. That makes it a little bit easier, right? And that's going to be equal to the natural log of VI over VF. Right? Now this implies, because it's natural log on the left, natural log on the right, right, that if we took, we could take e to the power of both sides. And this implies that TF over TI to the power of C, which is still this, is going to be equal to VI over VF. All right, they're going to be equal in this function here, right? And if we want to rearrange this, we can rearrange this into a couple different forms, right? These are all going to be equivalent. This is kind of our little base function here. We can rearrange it. Right? We can rearrange to solve for TF. We did that, right? TF would be TI times VI over VF to 1 over C, right? 1 over C. If you did the C root of everything, basically, right? That's what we do here. This is the C root, if you want to call it that, right? So our final temperature would be the initial temperature times this ratio, still to the same constant over here, right? Or we could rearrange it a little bit more, kind of split this part apart, right? And to make it something more like VI times TI to the C power equals VF times TF to the C power. Like if we, unfolded this to the C power and then moved everything all around, this is what we'd get. The same, it gets the same exact equation, just unfolded in different ways, right? Again, C is still CV over NR, right? CV over NR. Or another way you could say it is that, CV over N, that's the same thing as the molar heat capacity at constant volume, right? It's the same exact thing, right? Just depends on what numbers exactly you have. If you're given CB straight up, or if you're given CV, the molar heat capacity, right? And if you notice here, right, this is very close to sort of our Charles's law. If you remember Charles's law, right? Charles's law was, let me write this better. Right, that was V1 over T1 equals V2 over T2, right? That was Charles's law, one version of it, right? But the difference, of course, in this case relates to the conditions we're putting on it, right? We put a condition of adiabatic change. That's one big condition, which results in something very slightly different, right? Very, very slightly different. Right, so these are going to be the useful equations right here. Right, the useful equation, remembering that C is this. Right. Now we can also do something with pressure. Right. The pressure as it changes due to adiabatic expansion or in adiabatic conditions. Right. So the initial and final states of a perfect gas. Right, let's say P1 V1 equals nRT1 basically, or I. We'll call it I for initial. Right. That's always going to be true, whether it's final, right, or final or initial, right. And so since N and R are both constants, right, what do we see? We see that PIVI over PFVF is equal to TI over TF, right? Which is just, again, we're putting the ratio of the ideal gas law, basically, right? But we just figured out that TF, TI over TF, right, this right here, if we take this, we can figure out that TI over TF, right? If we looked at it, that would be equal to, what is this? VI over VF, 1 over C power, and then the negative 1 over C power, right? There we go. Yeah, if we put the negative inside here, we can flip the fraction kind of basically where it is right here, right? If we take this one and then, oh, sorry, not that one. We take, where is it? This result, right? Relating TI and TF, we get into this, right? Where we can plug all of this in for TF, right? And if we do that, right, rearrange a bunch of stuff, right? So we'd have PIVI over PFVF, right? That would be VF over VI to the 1 over C power, right? And if we rearranged all of that, it's going to be annoying, right? Then we would have PI for PF, right, times VI over VF to the 1 over C plus 1 power, right? Kind of annoying. And all that would equal to 1. And that's just a algebraic rearrangement, right? Doesn't look very pretty, but this is the end result. I'm not going to go through all the algebra because I don't care all that much about it, right? All right, so remember that C is still, right, CV, or let's do CV molar, right? This little constant C is CV molar over R. If we go from that, whoop, right, so we have, little c is CV molar over R, right? Well, if we go back to topic 2B about entropy, right? We said that at the very end of that chapter, of that section, that CP minus CV, right, is going to be equal to R, right? If we go back and look at it, it was CP minus CV equals NR, right? But when you divide both of these by N, you get the molar heat capacities. That's just what it is, right? We saw it as CP minus CV equals NR. Right? Divide both by N, we get the molar heat capacities. All right. Anyways, as we do this, right, our CV is going to be equal to R, what is it? Sorry, R, how do we want to do this? Let's do negative R plus CP M, something like that, right? So this gives us something to sort of, introduce, change our CVs into CPs, basically. All right, so if we were looking at what we had before, we had PI over PF equals VF over VI to the 1 over C plus 1, right? All that was equal to 1. So what we just left with, right? We're going to change C into something a little bit easier to use. We'll call it something easier to use, right? So this exponent here, 1 over C plus 1, right? That's going to be equal to 1 plus C over C, right? This is using our fraction properties, right? If 1 is going to be C over C, have a common denominator, we can add it all together, right? 1 plus C over C. All right. Our C, of course, is going to be if we put into this, right, CV over R. If we put it in, we get R plus CVM over CVM, right? And oops, CVM is, if we rearrange this, right, we could do CPM equals R plus CVM, right? The top is going to be CP, the molar heat capacity, constant pressure. The bottom is still going to be molar heat capacity, constant volume, right? So this entire exponent up here is going to be a much simpler version here of basically CP over CV. All right, and then we call CP molar in this case of each one. All right, we're going to give that the letter gamma. All right, gamma, lowercase gamma. And so when we rewrite this, instead of having, right, VF over VI to the 1 over C plus 1, we're just going to call this gamma now. Right, make it gamma. Makes it a lot easier. Right. Also, we have the heat capacities at constant pressure, constant volume, very easy to get. Right, very, very easy to get. And if we rearrange this equation to move things and spread it out on both sides, we can rearrange this to P1 V1 to the gamma power equals, or sorry, not 1, PI VI, PF VF to the gamma power, right? We spread it out. And this is, again, adiabatic expansion of a perfect gas, right? So again, this gamma here, the two things to remember, all right, we have our C, which is CV over NR, or CV molar over R. And our gamma, which is CP molar over CV molar. Keeping those things in mind. And if you look here, this specifically, if you look at it, it looks very, very close to Boyle's law. All right. Boyle's law, which was P1 V1 equals P2 V2, right? P1 V1 equals P2 V2. All right. Now we just have a little bit of a modifying factor here with the gamma. That's going to be altering these things a little bit, right? It's going to take into account how the internal energy changes, how the enthalpy and the internal energy change with regard to temperature, right? And for a particular substance, right? So that is going to be basically all for this chapter. There's a little bit of stuff at the end about, they say for a monatomic perfect gas, CV molar equals 3/2 R, and CP molar equals 5/2 R. I'm not going to make you remember that sort of stuff. Or I talk about what's a monatomic perfect gas, or a nonlinear polyatomic molecule, or all this other stuff, because we'll figure that stuff out in PChem 2 if we ever get to it. Right? Y'all are not going to get to it eventually, but some people will. Okay, and that's going to be the end of the chapter.